we're going to be looking at today is the Schrodinger's equation. It is one of the more interesting and one topic where you can actually score easily. So before we actually go into the derivation, this slide will tell us about the motivation behind learning the Schrodinger's equation and why it actually came about. So in a previous lecture we looked at wave-particle duality, which basically means any object in the universe can be described in terms of a wave or in terms of a particle, meaning every object has both a wave nature and a particle nature. So if this is not very clear to you, I would encourage you to go back and revisit the contents of the previous lecture. But for now, for time being, what you need to know is you take any object in the universe, it can be described as a wave or as a particle. So to describe an object as a particle, you need to specify its position, momentum and change in these two quantities with respect to time. That is what the first point in the slide says. So the state of a particle is well defined if you can specify its position, momentum and time evolution. Time evolution meaning change in position or change in momentum with respect to time. Similarly, if an object is supposed to be described as a wave, you should be able to specify its frequency, amplitude and change with respect to time. Change with respect to time is what we call as phase. So to describe an object as a particle, we need to know its position and momentum, and to describe it as a wave, we need to know its frequency and amplitude. But now what Heisenberg's uncertainty principle says is that accurate simultaneous measurement of position and momentum of a particle is not possible. So when we looked at let's say acoustics or light in school, we generally, when we're talking about waves, we use something like x equals a cos theta plus b sin theta plus phi or something. So where a is the amplitude and theta refers to the angular frequency or time period or something from which you can get the frequency. So both the amplitude and frequency are well defined in that equation when you're talking about a wave. But when we are talking about a particle, the Heisenberg's uncertainty principle says you cannot accurately measure both the position and the momentum at once. Meaning, if you know the position of a particle very precisely, then you do not know its momentum for sure. You'll know that the momentum is somewhere in this range, but you cannot pinpoint the exact value of the momentum. Or if you know the momentum for sure, you know that the particle exists in this neighborhood, but you cannot pin down its exact location in terms of coordinates. So that is what it says. You cannot know both the position and the momentum accurately at the same time. So what we do is, but we still need to describe a particle, right? So if you're going to study the motion of a particle or perform some operations on it, you need to describe it in terms of an equation. And because we cannot describe both quantities accurately at once, we talk in terms of probability. So we take one quantity, the quantity which we are sure of as an actual quantity, and for the other one we talk in terms of probability. Meaning, let's say I know the coordinates of a particle for sure. I know it exists at 0, 0 for sure. There is no doubt about it. But what is its momentum? I'm not sure. Then I'll say the position of this particle is 0, 0 and its momentum lies around this value with a probability of 0.95. Meaning I assume the momentum is this much and it is highly probable that this momentum is this much, but again I cannot say with 100% certainty. Or the other way around, I say I know the momentum for sure is this much, but the particle is most probably located in this neighborhood, let's say unit circle of radius 1 or something. So with maximum probability, I think the particle is located there, but again I'm not 100% sure. So we take one quantity for sure and the other we talk in terms of probabilities. So that is what the Heisenberg uncertainty principle tells us. Now in quantum mechanics, an object is represented by a wave function that has all pertinent information regarding its state. So before we look at wave function is basically a transformation of an input to an output, right? We've all studied functions in math multiple times. So If I say f of x comma y is x squared plus y squared, then I am giving it two inputs x, y, and the function transforms it into some value and gives it back to me, and that value is x squared plus y squared, or f of x equals sin x or something. So when we talk about wave function, it is again a function. It takes one of the characteristics of the wave as input and gives me back an equation from which I can derive any of the characteristics. So again, I'll explain this in a little more detail, but before that, we go back to our example of f of x comma y equals x squared plus y squared. Now the two inputs to this function are x and y, and the output is x squared plus y squared. So this is not strictly related to wave function, but just giving you an analogy to sort of help you understand. Let us assume x is position and y is momentum, and the uncertainty principle says we cannot accurately know both at the same time, right? So you know x and you know some range for y, then you pass it both into the function and you get back a value called x square plus y square. So you know x and you know x square plus y square, so from that you calculate y. Now this is not strictly how the wave function works, as in you can tell me if I don't know y, how am I getting x square plus y square back? That is not exactly how it works, but it is sort of an analogy to tell you that you don't know all the characteristics about the particle, but using the value of the wave function you can get back the characteristics you don't know. So if I know x and I know x square plus y square, I can get back y, right? Similarly, I know the position and I know the value that the wave function is giving me. Using that, I can get back the most probable momentum. And as an example, so that is what the wave function is. Basically, it is a function which tells us, which gives us all pertinent information about the particle, about the state of the particle. And how do we get those required information from the particle? That is what we are going to be seeing in the derivation. So for example, if my function is x square plus y squared and I wanted to get back y, I have to do root of this, okay, x square plus y square is my function. So function minus x square whole under square root, right? So if f equals x square plus y square, f minus x square whole raised to 1 by 2 will give me y. So similarly, I have a function and I do some mathematical operation on it and it will give me back the quantity I didn't know. That is what a wave function is. Except that wave function is complex first of all. So it involves I square root of minus 1 and related quantities. Secondly, it gives you all information about the particle. So potential, momentum, energy, position, location, coordinates, angular frequency, amplitude, all relevant information can be obtained from this one function. You have to perform a different mathematical operation to acquire each piece of information. What is that? We will be looking at it. So essentially, what this slide is telling us is, to describe a particle you need to know position and momentum. To describe a wave you need to know frequency and amplitude. For a particle you cannot know both the position and momentum with 100% certainty at the same time. So we usually take one quantity for sure, and for the other quantity we have this function called a wave function, using which we perform some mathematical manipulations and get back the unknown quantity. So that is what the wave function is all about.